Good morning, everyone, and welcome back to Math 115. So today we are going to discuss sections 1.7 and 1.8, and I'm really frustrated right now with our class, not you guys, but with the material, because for some reason I just feel like I'm way overscheduled for this class, and I have so much to cover. Come and grab your exams. Here. For some reason, I just feel like I'm way overscheduled, and I have like so much content to cover, and I want to cover everything thoroughly, and not skip over anything important or go too fast. So I don't know. I'm having a hard time with it. We'll probably have to skip some stuff later on, or else pick up the pace. But I'll try to do it in a way that it's as pain-free as possible for all of you. So that's what we're going to cover today. In terms of homework, you have a homework assignment due today on 1.5. So we covered 1.5 on Friday/Monday, I think. And 1.5 is also going to be on the quiz. So the quiz is coming tomorrow. So let me erase Thursday, September 22, and put tomorrow. Okay, so that'll be in the last 15 minutes of class tomorrow. I'm also going to post a homework for section 1.7 and maybe 1.8 soon. They'll probably be due on Sunday or Monday or something like that. So that's homework and quiz. One other thing I want to mention is I recorded my office hours yesterday. And basically, I'm going to record my office hours whenever I can and put them onto my YouTube channel. Sometimes it's not going to be possible, just depending on, like, if I'm in my office with one student, okay, I'm not going to record my office hours as I write on the board. But if we have a lot of people and we go to a classroom and I use my iPad, then probably I'll record. Okay? So the recording from yesterday is up on my YouTube channel if you want to check that out. We covered some stuff from 1.4 and 1.5. Those are the sections that are going to be on the quiz, so people had a lot of questions on those. Aside from my office hours, which are going to be tomorrow from 2:30 to 4, there's also the tutoring center. I sound like a broken record at this point, but please go there. All right, any administrative questions before we start in on content for today? No? Okay. Then let me remind you what we talked about last time. So last time we learned about all sorts of different functions, okay? So we talked about linear functions, square root function, the cube root function, piecewise functions, step functions, okay, and also our function celebrities, okay? So we learned the graphs of many, many different functions. And I recommended that you make flashcards for these because you will need to memorize these. For the purposes of quizzes and exams, you need to know how to graph these equations or these functions. So those are the functions that we needed to memorize, and then what did we learn? We learned how to transform those graphs using vertical shifts, okay, so moving up and down by adding on the outside. We also learned about horizontal shifts by adding by a number on the inside of the parentheses. And what was the weird thing about horizontal shifts? You put that into words?
If you're adding inside, you move it to the left.
Yeah. If you add inside, you move to the left. Oh, and that's confusing because we typically think, well, if I'm going up, then it's kind of like to the right. But in this case, when we add a number on the inside, okay, then we move to the left, okay? So for example, x plus 3 cubed. We moved our graph 1, 2, 3 units to the left. When we did x minus 1, we feel like that should go to the left, but it doesn't. It goes to the right. Okay, so that was the weird thing about horizontal shifts. Then we did a couple combination problems. And then we talked about reflection about the x-axis, okay? So this was when we have a mirror, right, on the floor, which is kind of weird, but if we had a mirror here, then everything that is on the bottom is going to go to the top, and everything that was on the top, okay, is going to go to the bottom, basically. Make sense? All right. Then we talked about, yeah, we did talk about reflection about the y-axis. Okay, so this was more our usual speed. I forgot to mention what causes reflection about the x-axis. It's a negative sign outside. Okay, so you're starting to notice everything outside has to do with the up and down world. Okay, whether we add, whether we make it negative, whether we multiply by a number. Okay, it's all going to correspond to the up and down world. And everything that happens inside the parentheses is going to be in the side-to-side world, okay? So that was reflection about the y-axis. So we have a negative on the inside. So how are we going to reflect? We're going to reflect side to side, right? And that means we're going to do like a normal mirror does, right? So in this case, we had f of x equals the square root of x. If I did f of negative x, okay, what would that look like? Well, if I made the equation, it would be the square root of negative x, right? And the domain of this function is actually the opposite of the domain of this function, right? Because we need negative x to be positive, which means we need x itself to be negative, right? So that we can plug it in, right? All right, so that was reflection about the y-axis. And then the last one we learned was absolute value. Okay, so the absolute value sign, remember what it does. If the function value is positive, i.e. the point lies above the x-axis, then the absolute value sign does absolutely nothing, right? But if the absolute value, or if the thing inside of our absolute value is negative, then it is going to take that negative value and make it to be positive, okay? So at the end, it basically just takes all the negative values, okay, and makes them into positive ones, okay? That's what absolute value does to a function. And that was where we stopped last time. So let me pause and ask if there's any questions on what we covered in class last time. All right, it doesn't seem like there are any. So we'll talk more about stretching and compressing. Okay, so there's two types of stretching and compressing. The first one we're going to talk about is when we do so vertically. Okay, so the way I like to describe stretching and compressing is I think probably everyone at some point in their life has made a Word document that they tried to put a picture in, yeah? And you know how Word doesn't like it when you try to put pictures in it, right? Okay, so in Word, okay, you get a lot of dots on your image, right? You get one here, and one here, right? The ones on the corners, when you resize, they resize in like a scaling way, right? But what does the one on the top do? If you use the one on the top, okay, basically it stretches or it compresses just in the vertical direction, and it messes up the way your picture looks, right? It makes it all squished or stretched out, okay? Or it's kind of like if you had a picture on like some rubber, right? And you stretch it like that, then it's gonna get real, stretched out, I guess. I don't know how else to describe that. But that's what we're gonna do now with vertical stretching. Okay, so the way it happens is if our function is multiplied by a number, okay? And depending on what that number is, okay, but depending on what that number is, then we may have a stretch or a shrink. Okay, so what do we want to say? We take the graph of f of x, but if the absolute value of a is going to be larger than 1, okay, so what numbers are larger than 1? Something like 2 or 3 or 4.5, okay? All of these types of numbers are going to produce a vertical stretch, okay, a vertical stretch. Why? Because we take the height of every point and we multiply it by a number bigger than 1. If I multiply a number by another number which is larger than 1, then the result will be larger than what I started with. Agree? Maybe that's too many words and not enough writing. If I take a number like 6 and I multiply it by 1/2, it will get smaller, yes? But if I multiply it by 2 or 3 or 4 or 5, it will get bigger, yeah? So if I multiply the height of the function by a number, it will get bigger if that number is larger than 1. And it will get smaller if that number that I multiply it by is less than 1. Okay, so what we're going to do is just multiply the height of each point on the graph by a. Okay, so i.e. if x comma f of x is on the graph, or you could say xy, whatever, then x comma f of x times a will be on the graph of the other one. So we take all the y values and we multiply them by a. All right? All right, let's see how that works. So the absolute value function, our old friend. How does that one look again? Like a V, right? I'm seeing people do it with their hands. Good. We got a V. All right. So here's what I'm going to do. I know I have the point 1, 1 on the graph of this function. And if I'm going to do 2 times the absolute value of x, well, the absolute value of x is what goes in the y spot, right? So in the y spot, I'm going to multiply by 2. So instead of having the point 1, 1, what is the point going to be? So if I'm going to transform this, it's going to be what? 1, 2, right? 1, 2, because the y spot is on the right side. So I'd put a 1 here, and I'd go up 2. I'm going to go through 1, 2 instead. So what's going to happen? It just looks like I took the thing and I stretched it out, okay? So where did I grab with my hands? I mean, I don't know. You could think like, okay, imagine that this was a hand. Okay, I'm going to grab here, and I'm going to pull in this direction. Yeah, that's what I'm going to do. All right, so this is the point 1, 2. Okay, how about if I multiply by 1/2? Then what's going to happen? Well, if I plug in 1, right? If I plug in 1, then what do I have here? Absolute value of 1, right? And if I take 1/2 and multiply that with the absolute value of 1, what do I get? 1/2, right? So the height of the point will be 1/2, because that's what I get when I plug the x value into the function. So it should be 1/2, right? So this is the point 1, 1/2. And my absolute value function looks more like this. Okay, so I squished it. Or I used the hydraulic press, like that guy from the internet back in the day. Okay, so it's a little bit hard to see. I probably should have exaggerated this for you. But this one, you can see is thinner, right? It's skinnier. And this one over here on the other side is wider, yes? Okay, so that is the effect of a vertical stretch or a vertical compression. Okay, so if the number is larger, it's a vertical stretch. If the number is smaller than 1, then it's a vertical compression or shrink, however you want to say it. All right, questions on vertical stretching? All right, then let's talk about horizontal compressing and stretching, and this is going to be the hardest one. Okay, the hardest one of all, probably. Okay, let's see why stretching and compressing horizontally is annoying. Well, we've already learned that everything that happens horizontally is really annoying, right? And what did we learn? We learned that when we do stuff on the inside of the parentheses, it feels like the opposite of what is supposed to happen. right? So the same thing is going to be true for stretching and compressing horizontally. So what do we do? Rather than multiplying by a number out front, I multiply by a number inside. Okay, I multiply by a number inside. And if that number is larger than 1 in absolute value, if the number is larger than 1, we're going to have a shrink, right? That's annoying, because when a is larger than 1 for a vertical stretch, we have a stretch, not a shrink, right? So it's backwards when we do it horizontally. If the number inside is bigger than 1, we think, oh, big number, that makes things bigger. But actually, it's going to correspond to a shrink. Okay, so remember, everything that happens inside those parentheses, it feels like it's doing the opposite of what it should. Okay, so we shrink horizontally by a factor of a. And if a is smaller than 1, so something like 1/2, okay, if a was a half, then that's going to correspond to a horizontal stretch. My God, that's annoying. Right? Okay, so let's see how it works. Well, generally speaking, what we are going to do is we are going to multiply all of the x values of our points by 1 over a. Okay, so if xy is on the graph of f, okay, let's not cut corners, on the graph of f of x, right? If xy is on the graph of f of x, then x over a, comma y, so same height, different x value, is on the graph of f of a times x. Okay, so it's really confusing because we're multiplying by a, but all the x values are actually going to get divided by a, is going to be the effect. Okay, if you want some intuition on why that makes sense, here's maybe my best effort at a description. If I do f of x, right, and here's x, right? So if I plug in x into f of a times x, what I actually have to fetch is the x value which is much further away, right? Here's a times x. And then the height, when I plug in x into f of a times x, is going to be the height of the original function, okay? The original function at when I plug in ax. So I need to move it over, right? And inwards, I guess, as long as a is bigger than 1. So maybe that's a really bad description, but basically what I'm doing is I'm fetching x values. If a is larger than 1, I'm fetching x values which are much further away and bringing that height closer to the origin or to the y-axis. All right. That is kind of unintuitive the first time you see it, so don't feel bad if you don't quite understand that. Let's just see how it works if we want to do some examples. Okay, so this time they don't give us a function, do they? They just give us the graph of the function. All right, just the graph of the function. We could probably come up with like a piecewise function here. It'd be like a parabola. Okay, forget about it. What we want to know is how do we stretch it? Okay, how do we stretch it? Well, remember, when I am doing multiplication by a number on the inside, okay, if that number is bigger than 1, am I going to have a horizontal stretch or a horizontal compression? I'm going to have a compression, right? Okay, so the number is bigger than 1. So what are we going to do? We're going to take this picture and we're going to squish it, like shown, right? That's what we're going to do. Okay, so I know that the point 1, 3 is on the graph of f of x. So what form is that point going to take on the graph of f of 2x? How is that point going to change? It's not going to be 1, 3. It's going to be something, comma, something. How should it change? Well, let's ask ourselves. this component describes the height. If I multiply by a number on the inside, am I changing the height? No, I'm not changing the height. So the height of this point should be the same. And what should the x value of that point be? It should be 1/2, right? Okay, so we take the x value of all the points and we divide it by whatever that number is. Okay? So the point 1/2, 3 is going to be on the graph. Okay, and how about the point 2, 0? Where's it going to go? It's going to go to 1, 0. Yes? And how about the point 0, 0? Is it going to move? No, why not? Yeah, but I still have to divide the x coordinate by 2, right? Why doesn't that change it? Because this is the point 0, 0. If I take 0 and I divide it by 2, it's still 0, right? That's why it doesn't move. Okay, so still 0, 0. And how about this point here is -2, -1. Where's it going to go? So this is -2, -1. What are we going to do to the x value? Divide by 2. If I take -2 and I divide by 2, what do I get? -1. Okay, so -1, 1. Okay, so now we can put our picture together. It looks something like this. Okay, so we took this whole thing and we squished it, left and right wise. And we didn't move it whatsoever in the up and down direction, did we? We only squished it left and right. All right. Let's see how it works when we divide by a number. Well, if I divide by a number inside here, what am I going to do to the x values? I'm going to take all the x values and I'm going to divide by whatever that number is inside, right? What's the number inside right now? It's 1/2. Okay, so I'm going to divide by 1/2, which is the same as multiplying by 2. Okay, so we're going to divide by a fraction. Okay, so you could also view this as f of 1/2 times x, right? That's what I'm trying to say here. The a value, it's less than 1, meaning we are going to stretch in the horizontal direction by a factor of 2. Okay, so instead of having 1, 3 on the graph, what's going to go on the graph is going to be 2, 3, yes? And instead of having 2, 0, I'm going to have the point... What am I doing? Okay, we're going to have the point 4, 0, right? And 0, 0 is not going to move. And how about on the left side? Should I just move it 2 over to the right? What should I do instead? I should not move 2 to the right. I should move 2 to the left, right? I take -2, the x value. I divide it by 1/2. -2 divided by 1/2 is the same as -2 times 2 over 1, which is the same as what number? -4, right? 2 times 2 is 4. Okay, so this one goes all the way out to -4. And the height doesn't change. So in this picture, it looks more like this. Okay, that wasn't very good, was it? That's better. Okay, so the whole thing got a lot wider, okay? A lot wider, as opposed to the first one, where we made everything thinner. Okay, so any questions on horizontal compressions and stretches? All right, then let's talk about how to combine every single one of these compressions and stretches and shifts and reflections all at the same time. Okay, so This is my most colorful slide that I think I ever made. But I tried to color coordinate it with how the steps go, okay? In terms of what are we going to do first, okay? So let's say I have f of x, and I transform it into a times f of bx plus c, n parentheses, plus d, right? So I have one of basically every single type of transformation shown, okay? So what would be an example? Something like 2f of negative 3x plus a half minus 7, okay? That would be an example. So what do we have? We have a horizontal shift by a half to the left. We have a horizontal reflection because this is a negative number, and also a horizontal compression because this is the number 3, which is larger than 1. And also we're going to have a vertical stretch, and also we're going to have a vertical shift. So we got all these different types of things going on. So what order am I supposed to do them in? Okay, and there's not really a good way of memorizing this order, at least not that I know of. Maybe you all can come up with a cool mnemonic device. But all I know is to memorize it, basically. So, okay, what do we do first? First, we do the horizontal shift, okay? That corresponds with C, okay? Horizontal shift corresponds with the number C. Then we do a horizontal stretch or compression, if there are any, okay? If there aren't any, we just get rid of this step, all right? So horizontal stretch comes next. That's B, okay, the number B. Then we do the vertical stretch, okay? That's the number A. Okay, and then we apply any relevant reflections, okay? That means after we've already stretched or compressed horizontally, stretched or compressed vertically, then we are going to apply any flips that we need to do, okay? So any mirroring via this reflection stuff. Okay, and then lastly, we have the vertical shift. That's going to be the last thing that we do. Okay, so this is the order of the steps that we do for transformations of functions. So I'm going to do an example now of a function with a lot of different transformations that we have to track all of them. But is it okay for me to move on from this page? See Lauren taking a picture, so I'll wait for that. Is it okay for me to move on, or does anybody need a little more time? Oh, now everyone's taking pictures. Okay. I'm going to move on now. It's in the recording if you want to go back and check it. Or in the notes, which I post to Blackboard. Okay. So this looks scary. We've got a ton of different transformations going on here. Okay, we've got negatives, we've got multiplications by numbers, so we're stretching. We've got shifts to the right and also shifts happening to the upward direction, right? So at the end of the day, this is going to look crazy, right? Totally crazy. Okay, well, let's see how it works. The first thing that we're supposed to do is the horizontal shift. So let me switch to pink and we'll apply that shift. So first off, horizontal shift. So what does the shift do? It moves us 1 unit to the right. Okay, that's confusing. It's a -1, but we're going to move to the right, okay? So what is going to happen to our picture here? You know what I should do? I should just copy. It would be so much smarter if I just copied this. I feel like that would be way smarter. Okay, so what are we going to do? We are going to redraw this, except we're going to move everything over to the right 1 unit. So it's going to look instead, it's going to look like this. Yeah? Okay, so we moved it over to the right. Okay, now let's do it again for the next thing. So this was step 1. Step 2 is what? Horizontal stretch or compression. So step 2, let me get that lime green. Step 2, we do horizontal, is it going to be a horizontal stretch or is it going to be a horizontal compression? What do we think? Compression, right? Okay, so we're going to do compression because the number inside is bigger than 1. So we're going to take this picture now, and we're going to compress it. Okay, we're going to compress it. So what would that look like? Well, instead of going from -1 up to 0, this segment is going to go from -1/2. And the height isn't going to change at all. Okay, and instead of going from 0 to 1, this segment's going to go from 0 to 1/2. So it looks like that. And then instead of going from 1 to 2, this segment is going to go from 1/2 to 1. So now it looks like that, right? Okay, so that's the horizontal compression done. What's up next? Vertical stretch or compression. Okay, so let me get the red out. So 3 is vertical stretch, right? No, it's a vertical compression. Why is it a vertical compression? Because this number is smaller than 1. So remember, horizontal compression, the number will be bigger than 1. For a vertical compression, the number should be smaller than 1. So we're going to do a vertical compression. Okay, so I didn't label the height here, but let's say that this height here was 1. What's the new height going to be? It should be 1/2, right? So let's take this picture now, and what we're going to do is we're going to take this height and basically we're going to squish this thing by a factor of 2, right? So instead of going up to 1, it's going to go to 1/2. So we start at here and we go up not to 1, but to 1/2. And then we go over and then we go down. Yes? So what happened from here to here is we squished in the vertical direction. Okay, we squished in the vertical direction. All right, now what? Reflections. Do I have any reflections? What do we think? Who says yes, we should do at least one reflection? Okay, I'm seeing a lot of hands. Can one of you explain why we should apply a reflection? Because there's a negative, and that negative happens to be on the outside. Okay, and all the stuff on the outside, what does that have to do with? Left and right or up and down? Left, it's up and down, right? If we're on the outside, we should always be dealing with up and down world. So if I have a negative sign in the up and down world, I'm going to do a reflection. Can anyone tell me what axis I'm going to reflect about? I hear Y and I hear X. Who says Y-axis? Who says X-axis? Okay, some more for the X-axis, right? Okay, here's the deal. It's a little bit confusing because we're going to change the Y values. But that means that we are going to reflect over the X-axis, okay? So I think that may be one of the confusing bits here. So let's see how it works. So next up is we have a vertical reflection. So all we're going to do is we're going to copy the picture from the side of us, and instead of drawing it like that, we're going to draw it upside down. Okay, so now we're here. All right, and then the last thing to do is the vertical shift. Do I have a vertical shift? Yeah, the +3, right? If I add something on the outside, that produces a vertical shift. And the vertical world is very easy to understand, right? Up means positive, right? So we like doing vertical shifts and vertical stretches and all these things, right? So up 3 is the last step. So let's erase that and go to, I think I used white for the vertical. So the 5, we do a vertical shift. So we need to move up 3 units. Okay, so here's 1, 2, 3. No, I shouldn't draw them like that, should I? Why don't I make them like 1, 2, 3? So we should start at the point -1/2, comma 3, yes? So that's this point. Oops, it's more like that point. Okay, is -1/2, comma 3, yeah? And then what should we do? We should go down by a 1/2 unit. So we go down by a 1/2 unit. Okay, and then what should we do? We should go over 1/2 unit. So that takes us over 1/2 unit. And then what should we do? We should go up a 1/2 unit, like shown. Okay, so it got a little, my picture got a little wonky at the end there. But what did we do? We just took this and we moved it up 3 units. Okay, so that's the order of the transformations that we need to do. So when you see something like this, I think it looks really scary. But if you take the steps one by one, I don't think that any of the individual steps, I hope that none of the individual steps are that scary. We just apply them in order, and we just keep on trucking, we keep on swimming until we get to the end. So any questions about how I walked through that example? Okay, I just want to reiterate one more time the rainbow slide. Order matters, okay? If I accidentally do the vertical shift first, it's going to totally spoil everything, okay? So I need to make sure that I apply the transformations in the correct order. All right? Okay. So let's talk about section 1.8 now. Let's see how much time I have. God, I feel like I have no time to do anything in this class. Okay, it's fine. Everything is fine. All right, let's talk about combining functions. So last time we talked about how to take a single function and switch it up a little bit, right? Move it up and down, stretch it side to side, these sorts of things, right? But now we're going to talk about, well, if I have 2 different functions, okay? If I have 2 different functions, like f of x equals 2x, and then g of x is a different function, it's maybe x squared. Well, how do I combine the 2 of them, right? How do I combine the 2 of them? Well, if I look at their graphs, right, x squared looks like a parabola, okay? And then x looks like, 2x looks like a line like this, right? So we want to know, how are we going to add these 2 functions together? Well, all I'm going to do is I'm going to take the height of one and I'm going to add it to the height of the other, okay? And I'm going to get a new height, okay? That's basically how I'm going to combine functions. So that's exactly what this says. F plus or minus g of x is equal to f of x plus or minus g of x, okay? So this is just notation that we use. Sometimes I'll write f plus g of x. What I mean is this, f of x plus g of x, okay? Or if I do a minus here, then I do a minus here, okay? So in that case, it would be, for this one, for the example, it would be x squared plus 2x, or minus, okay? Easy peasy. All right, if I write fg of x, then that means what we call point-wise multiplication, meaning for each point on the graphs of f and g, okay, for each x value, I take the height of the one and I multiply it with the height of the other for every x, okay? So, for example, in this case, the way I would do that is I would take 2x and I'd multiply it with x squared, right? If I took 2x and I multiply with x squared, can I simplify that? What would I get if I simplified? 2x cubed, right? What would I do when I multiply powers of x? You add the powers. Since 1 plus 2 is equal to 3, we get 2x cubed when we multiply 2x times x squared. All right. So next up we have division. Okay, if I write f divided by g of x, then what I mean is for every point, by which I mean every x value, I'm going to take the height of f of x, and I'm going to divide it by the height of g of x, and that's going to be the height of this new function. And that new function is going to be easily expressed by 2x divided by x squared, which of course can be simplified, can't it? How can I simplify? Move the x squared to the top and make it negative. Okay, so we get 2x times x to the minus 2, which is what? Two x to the negative 1, right? Which would be 2 over x. Okay, I think a simpler way would probably be to move this x down as an x to the minus 1, yeah? And then combine these two with the addition rule, right? 2 minus 1 is 1. So we get 2 over x, right? Or just cancel out 1 power of x if you want to. You could say, well, this is just x times x, right? So I just cancel 1x here and 1x here, and I'm left with 2 over x. All right. So that's simplifying that. And now let's talk about the domain. Okay, so the domain and range of combinations of functions is a delicate matter, kind of. So here's why. If I want to plug a number in to f plus g of x, I need to be able to plug that number into the function f, and I need to be able to plug that number into the function g in order for this to make sense. So the only numbers which are going to be in the domain of f plus g are going to be the numbers which are in both the domain of f and the domain of g, okay? So in that case, the domain is going to be, this is, okay, domain of f. I'm going to write as d of f for now. And then d of g is going to mean domain of g. Okay? So I take the domain of f and the domain of g. I need the number to be in both of those two things. So I use the intersection symbol, okay? The intersection symbol, okay? To denote this new set is the set of objects which are in both of these two, okay? Which are common between these two. Okay, the only other exception for these ones is the quotient, okay? When I do f divided by g of x, yes, I need to be able to plug x into f. Yes, I need to be able to plug x into g. But I also need to make sure that when I plug x into g, I don't create a 0. Because if I create 0 in the denominator, well, we don't like 0 in the denominator, do we? Okay. So we exclude those values which make g of x equals to 0. Okay, so let's see an example. Let's combine these functions and find their domain and range. So, well, let's just find their domain. We'll talk about range another time. Okay, so if I take f plus g of x, what am I going to get? I'm going to get x squared minus 6x plus 8, and then plus x minus 2, right? And I should always add functions using parentheses, okay? It's probably safest just to put parentheses around each function. Okay, so in the end, I get x squared minus 5x, and then 8 minus 2 is plus 6, yeah? Okay, so this is my new function, right? So, what is the domain of f? What sorts of numbers can I plug into the function x squared minus 6x plus 8? Are there any that I can't plug in? When do I worry about plugging something into a function? There's two situations where I need to be careful. What are those situations? If you're dividing by 0, that's the situation number 1. And number 2, Connor's got it, it's the square root. So, do I have any division here? No. Do I have any square roots here? No. So the domain should be all real numbers. Okay, and how about this one? D of g, what's it going to be? Yeah, it's going to be all real numbers again, right? Because, I mean, you can put whatever number here. This is not going to cause any problems. Yeah? All right, so that's domain of f and domain of g. So domain of f plus g is going to be the domain of f intersected with the domain of g, which is going to be those numbers which are in the reals and also those numbers which are in the reals. What do I get if I take one set and I intersect it with itself? Just itself, right? Okay, it's like, okay, I want x to be a real number and I also need x to be a real number, right? Those two things are the same. So if I intersect a set with itself, I just get itself. All right, so that's pretty simple. I'm going to skip the other ones except for the quotient. Let's do f over g of x. Well, if I do this, then I get f of x over g of x, right? Which is, of course, just going to be x squared minus 6x plus 8 divided by x minus 2, right? Divided by x minus 2. And I see immediately that there's going to be a simplification that I can do here, right? How can I simplify that? I can factor the top. How does the top factor? X minus 2 and x minus 4. And I divide by x minus 2, so I can cancel those, right? Okay, and so now I have x minus 4. So let's talk about the domain. What sorts of numbers can I plug into this function? All real numbers, right? So, question for the class, is the domain going to be all real numbers? No. Why not? Because we can't plug in 2, okay? We have simplified this function, okay? But we have to remember where it comes from, which is this. If I plug in 2 into this equation, I get 0 divided by 0, okay? Which is not defined, okay? So I need to use the rule. What does the rule say? It says the domain of each is going to be the intersection of their domains minus any numbers which make g 0. Okay, so in this case, it's going to be d of f cap d of g, and then I'm going to set minus x equals 0. Not 0, x equals 2, right? So in this case, I get all real numbers minus the set 2, which can also be expressed as negative infinity up to 2, comma, 2 up to infinity, not comma, union, right? So this is r cap r. Okay. So that's where I'm going to stop for today. So thanks for your attention. I'll see you all tomorrow for the quiz.